Okay, so let's move on here and talk about section 5.3. Which is about factors and primes. Okay, so the key ideas in this section. So know what it means when I say a prime number versus a composite number. Okay, be able to find prime factors. Know how to make factor trees. Okay, these two concepts are of course related. We will use these factor trees to help us find the prime factorizations of these numbers. And when we're doing these factoring, try to build on what we've already done. In other words, try to use the divisibility tests to help us see if something is a factor. I'll show you what I mean with a couple of examples. Okay, let's start out with this right here. So, a factorization or a factoring of a number n means writing n as a product. Okay, in other words, we're finding two numbers that we can multiply together and get n. So we're starting with some number, whatever it is. We're trying to find two other numbers that multiply together to give us n. Those numbers are called our factors. A prime number only has itself and 1 as factors. Okay. 0 and 1 are not considered primes. I'll show you why in a little bit. So a number is prime if it only has itself and 1 as factors. Otherwise, it is composite. Let's warm up with some examples here. So we'll start with a number and then we will list all the factors of that number. Okay, let's do this one here, 12. Okay. Now, 1 is always a factor, okay? We could always use 1 as one of these numbers, and then we just put the starting number right here, okay? So we could always do that. Okay, now, here's the thing. When you're doing a list of all these factors, it pays to kind of be systematic. You can't find just one factor. It's always got a partner. It's always got this thing over here. Okay, so if 1 is a factor, and I was to write 12 as a product of 1 and something else, then the something else would have to be 12. Okay, so I get 2 factors. Now, this is even, of course, so 2 is a factor. What's the factor that goes with 2? 6. Okay? So I'll write that one over here. Notice kind of I'm working from both sides. All right? So what's the next thing that this is divisible by? Let's think kind of in order here. 3 goes into 12, right? And what's the other factor? 4. Okay? Whoops. Jumped the gun there. 3 and then 4. And those are all the factors. Okay? You might say, well, it's divisible by 4. Yeah, we got that written down. Okay, because we're kind of doing it systematically, working from both ways in. All right, I want you to take a moment in your seats. I want you to do that same exact thing for 36. I want you to write all the factors of 36. Give me a list of every number that divides into 36. Try working from both ends. You know you can start your list with 1. And then you can put a 36 on the other end. Give yourself a little space in the middle to do the other ones. Probably need a little more space than I had with this right here, but it's not like the list is super long. Okay, this is also even. Of course, it ends in a 6. So 2. What's the partner? 18. Okay, 2 times 18 is 36. This is divisible by 3. 3 times 12. Does 4 go into that? I think so. Yeah, 4 goes into 36. What's the partner? 9. Okay, 5, should that be on the list? No, 5 does not go into 36, it ends in a 6. The only way a number can be divisible by 5 is if it ends in a 0 or a 5. How about 6? Yes, what's the partner? 6 itself. Okay, so 6 is a little special in that 6 is its own partner, but that also means we've kind of reached the end, right? Because if you're saying, okay, well, how do you know we don't have anything bigger? Well, we would have found the partner of the bigger things over here. Okay, so you only have to go like halfway when you're doing this list of factorings. In fact, we'll see later that it's the square root of this number. It's not a coincidence that if I take the square root of 36, I get 6, and that was where we were able to stop. Okay, that would be important when we're doing bigger numbers. If we're checking to see if something is a prime, we only have to check up to a certain cap, and then we can just stop. So, in particular, if we haven't found something by the time we get to a cap, then we know we're done. So let's try this. Let's try 43. Okay. So we know it's divisible by 1 because everything is. Now, 1 and 43, okay. Is it even? No, it ends in a 3. Is it divisible by 3? No, it's not. A couple of ways we could do it. 4 plus 3 is 7, not divisible by 3, okay? Right? Because I know when I learned my multiplication table in 3rd grade, they made us do it up to, I think, 10 or 12, I forget, right? But I didn't learn my multiples of 36 beyond 12, okay? But I know this isn't, because I can do my divisibility test. How about 4? Nope. Closest is 44, that's 4 times 11. This would leave a remainder of 3 if I divided by 4. How about 5? Nope, ends in a 3. How about 6? Nope, because we checked 2 and 3 already. So the only way for this thing to be divisible by 6 is if it was divisible by 2 and 3. Now I have no idea what the square root of 43 is. Some decimal number, right? I could use my calculator. But I know it can't be any bigger than 7. How do I know that? I just said I didn't know what it was. How do I know it can't be bigger than 7? What's 7 squared? 49, okay? So if I take something that is bigger than 7 and square, I'm going to get something bigger than 49. Okay, so I know whatever the square root of this thing is, it's got to be less than 7. Is this thing divisible by 7? No, it doesn't go in. You can check it. But anyway, so those are the only 2 factors, which means that 43 is a prime, okay? So we're going through a list of these small numbers and checking if they divide in evenly. If they do, then we know we've got a composite. 12 is composite, 36 is composite. You can take any of these guys and pair it up with their partner and get 12. Any of these guys paired up with their partner gives you 36. So lots of factorings for 12 and 36, but the only factoring you can get for 43 is 1 times 43. Okay. Let's do some examples of factor trees. Oh, okay, here's one thing here. Fundamental theorem of arithmetic. Any number is either a prime or can be expressed as the product of primes. This product is unique up to order. Okay. So any number is either a prime or a product of primes. So basically we're saying that the classes of numbers that we discussed at the top exhaust all the numbers. You either fit into the class of primes or you fit into the class of composites. The class of composites can be expressed as a product of primes. Now this bit here, unique up to order. That means, let's say I do a factoring and Madison does a factoring. Okay? Madison can't come up with 7 primes that multiply to her number, and I come up with 6. Okay? We've each got to have 7 primes. You can scramble them up because the order which we did our factoring might have been a little different, but you can't get more primes. That's why 1 is not considered a prime. You can always throw in a factor of 1. No matter what you've got, you can throw in extra 1s. So we don't consider 1 a prime because then we would lose this unique number of prime divisors here. 1's a little too special, basically. Okay, so let's knock out some prime factorings by using factor trees. Factor into primes using a factor tree. Okay, let's try this one. 280. Okay, now you probably remember the concept of a factor tree from your school days. Okay, it's kind of, remember, mathematicians are not creative with names. It's a little tree. We put these branches going out. And on the branches we put factors. Okay, now my advice when you're doing this is try for the biggest factors you can do at the beginning, okay? This is even, yes, and I can pull out a factor of 2, but if I'm doing it like that, the process will take, the tree will get longer. And the issue with that is when you're making the process longer, you're throwing in more steps, extra chances of making a mistake, okay? If there's 7 steps, well, that's 7 ways this thing could go sideways. If we can do it in 2 or 3 steps, well, then that's less likely that we'll make a mistake because we've only got to do 2 or 3 things. All right, so I'm seeing, okay, this is divisible by 10. Right, that's easy to see because it ends in a 0. Okay, now there's only 2 factors of 10, 2 primes. These are both primes. I can't break the 2 or the 5 down any further. Okay. 28, that's divisible by 4. And of course I could break up the 4 into 2 times 2. Okay, so 280 is equal to, now here's what I'm doing with this. 2 cubed, remember your exponents? Right, I've got 1, 2, 3 factors of 2. 2 power 3. Times 5 times 7. Okay, so that is the prime factorization of 27. And that's unique up to the order in which we write them down. In other words, if somebody comes up and says, oh, I found 11 on this list. Well, something went wrong. Because if you throw in an 11, you're going to get something different than 280. It's unique up to order. You can't throw in new primes. Okay. So let's do another factor tree. Maybe something a little bit bigger, where we make use of our divisibility tests. How about this? 3,528. Okay, 3,528. So let me think of the biggest numbers I can do here. Is this thing divisible by 9? How could I figure that out? Is there a quick way for me to do that? Right, we add those digits up. So let's add them up. What do we get? 18. So this number is divisible by 9, right? So 3 plus 7 is, gosh, 8. 3 plus 7, what the hell? 3 plus 5 is 8, plus 2 is 10, gets me to 18. Okay, so 18. So divisible by 9. Is it divisible by 4? So what are we looking at for divisibility by 4? We're looking at these last 2. Okay? So we're divisible by 9, we're divisible by 4. So I'm going to factor those out together. 4 times 9. Now what's the other one? Well, I'm going to have to do a division here. 4 times 9 is 36. Okay, now if we're thinking about our division, we're thinking about estimates. Okay, so what am I picturing as this number? I'm not picturing 3528. I'm dividing by 36. It would be nice if this was 3,600, okay? That would make the problem really easy. Then it would be 10. Okay, it's not 3,600, so I can't really fit 10 copies, so maybe I can fit 9 copies. Okay, how do I multiply by 9 again? How do I do my mental math for multiplication by 9? Multiply by 10, so I got 360. Now what do I do? Take away 36. So 360 take away 30 is 330. 3, 2, 4. I do my subtraction here. 4, 12, 8, 288. Okay. I'm looking at 36 going into 288. Let's try 8 of them. Okay, 36, double it, you get 72. Double 72, you get 144. Double that, you get 288. Okay, 36 times that is 288. So this is 98. Okay, now the neat thing about doing it this way is I can factor these into primes very quickly. Okay, let's see, 98, well, I know it's even. The other factor is 49. 2 times 49 gives me 98. And this is 7 times 7. So my factors of 3, 5, 2, 8 are 2 power 3, 3 power 2, 7 power 2. Why is it 2 to the third? Didn't I just say 2 squared right here? Right, there's another 2 on the other branch, so we got to kind of count up all those 2's. Okay, so I want you to read through in Elementary Math for Teachers. Read through Chapter 5, Section 3 about primes and the fundamental theorem of arithmetic. That is on pages 118 to 120, okay, just 3 pages. On page 121, I want you to look at 1 through 4 and 7. 1 through 4 and 7. Okay, you guys in Zoom land, you're going to have your quiz 10 next time.